Okay, in this segment we're going to continue looking at a couple of examples of computing per unit sensitivities, and we're going to look at how per unit sensitivities combine to how per unit sensitivities combine in different senses of the word tolerance to comprise the tolerance of certain parameters in our circuits. So our second example is going to be resistors in parallel. And so we have this idea that if we have a bunch of resistors R1 up to Rn connected in parallel, that's equivalent to a single resistance Req, which is R1 parallel parallel R sub n. And for computational purposes, this is equal to the reciprocal of the sum of the reciprocals. And we're going to use this way of expressing it in order to do the required calculations. So we're interested in the sensitivity of Req to Ri, and that's again equal to Ri times the logarithmic derivative of log Req with respect to Ri. I guess I should have mentioned last time that when I write log in this class with no subscript to indicate the base, by default I mean the natural log. Log to the base e, and not the common logarithm. So that may strike you as kind of funny, but if you have ever tried to use MATLAB or Python and try to get the natural log, what you would find is that that function is actually called log in those packages, and not ln. And log to the base 10, the common logarithm, is denoted by log 10. And so in this class, when I write log, I mean log to the base e. So that's an aside. But this is, taking this out one step, this is Ri over Req, because the derivative of log Req is 1 over Req times d Req dRi. And so we can write this as Ri over Req, and we're going to use this expression here for Req, and so when we differentiate that with respect to Ri, we have this whole thing raised to the minus 1, so that we have a minus 1 coming out front, and then we decrease the power by 1 to minus 2, and so we have this is equal to minus the sum I equals 1 to n of r sub I to the minus 2. And then we apply the chain rule, and we have to differentiate, sorry, this is to the minus 1. We have to differentiate Ri to the minus 1, and that's going to be equal to minus 1 over Ri squared. Okay, so there's a couple of things that happen here. One is that we have minus sign times a minus sign, so that becomes a plus, and then this cancels with one of these, and we're left with basically 1 over Ri, that's this one that was left over, times 1 over Req, times, well, we can write this minus second power of the sum of the reciprocals of Ri as sum I equals 1 to n of Ri inverse to the minus 1, all raised to the minus 2. I'm sorry, to the 2. Right, so this is just Req. So this is Req squared divided by Ri times Req. And so that cancels with that. And so we get that this sensitivity is just Req divided by Ri. So this is just the reciprocal of the sensitivity of the series combination with respect to Ri. Okay, so last time we had an example at the very end where we're trying to make a 500 ohm resistor out of a 499 ohm resistor and a 1 ohm resistor, and we found that that 1 ohm resistor doesn't contribute very much. The equivalent resistance is not very sensitive to per unit variations in that 1 ohm resistor, whereas it's very sensitive to, in fact, it's almost completely determined by the sensitivity of the per unit sensitivity, the per unit variation in the 499 ohm resistor. But if I have a parallel combination of two resistors, suppose I have like, I don't know, a 909 ohm resistor, and I would like to make that into a 900 ohm resistor. So this is the closest 1% standard resistor value to 900 ohms. And if we wanted to knock that down to 900 ohms, we could put that in parallel with some larger resistor to shift its value down by 9 ohms. And it turns out that if we put in a 90.9K resistor, 909 ohms in parallel with 90.9K ohm resistors is exactly equal to 900 ohm resistor. And so if we like, we can look at what is the contribution of the per unit variation in this 900 ohm equivalent resistance to this 909 ohm resistor's per unit variation, and what is its sensitivity to per unit variation in the 90.9K ohm resistor. Well, for the 909 ohm resistor, it's going to be weighted by 900 divided by 909, which is pretty close to 1. Whereas this 90.9K ohm resistor is going to be weighted by 900 divided by 90,000. So it's going to be knocked down by quite a lot, right? So that's that says that we could, if we wanted to have, let's say, plus or minus 0.1% again, we could use a plus or minus 0.1% resistor for that one, but we could use a plus or minus 1% resistor for that one quite comfortably. Just as a side note, it may never have occurred to you to synthesize desired resistor values by using parallel combinations, but actually parallel combinations are actually quite nice because they don't create extra nodes in the circuit. And so, for instance, suppose we were interested in getting integer values of resistance or something like that. So the standard resistor values, let's say in the 100 ohm to 1K ohm range. So 100 ohms is in the standard set of values. It's called the E96 series of values. So this is exactly, it's in the E96 series exactly. 200 ohms is in the E96 series. Okay, the nearest value to 300 ohms is 301. So 301 in parallel with 90.9K. So these are both standard values. 909 is the closest value to 900. 90.9K would be the closest value to 90K. This is equal to, or it's approximately equal to 300.007 ohms. So it's pretty darn close to 300. And so if we were to put a 90.9K ohm resistor in parallel with a 301 ohm resistor, we would get something pretty darn close to exactly 300 ohms. 402 ohms is the closest E96 value to 400, and if we put that in parallel with 80.6, this is about 400.005 ohms. Again, pretty darn close to 400. 499 is the closest E96 value to 500 ohms. And if we put that in series with 1 ohm, which is also in the E96 series, that's exactly equal to 500 ohms, like we had in our example from last time. 604 ohms is the closest E96 value to 600, and if we put that in parallel with 90.9K ohms, that's about 600.01 ohms. Not quite as close as these two to their respective values, but close enough. 698 is the nearest E96 value to 700 ohms. Of course, if we put that in series with a 2 ohm resistor, that's exactly equal to 700 ohms. These are both standard E96 series values. If we like, we could use for 800, we could use an 806 ohm resistor, which is the closest E96 value to 800. And if we put that in parallel with a 100K ohm resistor, that's going to be 799.56 ohms, which is pretty darn close to 800. Certainly within 0.1% of 800. And again, 909 ohms is the closest value to 900, and if we put that in parallel with a 90.9K, we get exactly 900 ohms. So if we have these values, 100, 200, 301, 402, 499, 604, 698, 806, and 909 in each of the decades, we can actually synthesize values that are very, very close to the values that we're targeting here by either using appropriate series combinations of these values or parallel combinations. And there's sort of a closure here, which is kind of a nice thing. So that's just an aside to keep in mind. Okay, so our next example for computing per unit sensitivities is going to be a non-inverting amplifier made with an op-amp. We're going to look at the sensitivity of the gain to the two resistors that determine it. So here we're talking about an op-amp circuit that looks like this. Some input voltage V in. We have a resistive voltage divider down to some reference voltage V ref, an R1, R2, and this midpoint here is fed back to the inverting input This is V out, and then the op amp, as long as if the output is not stuck at one of the rails, because this op amp, the way this op amp works, we know that the inverting input will be very, very close to V in, and so the drop across R2, which is V in minus V ref, should be a voltage divider ratio times the drop from V out to V ref. So we know that V in minus V ref, the drop across R2, is going to equal the voltage divider ratio, which is R2 over R1 plus R2 times V out minus V ref. And we can rearrange this and solve for V out. This, actually, let me not label that right now. So to solve for V out, what we're going to do is multiply both sides by the reciprocal of this voltage divider ratio. And we can add V ref to both sides to isolate V out, flip it around, and we find that V out is equal to V ref. V ref is sort of the zero level, so when there's no difference between V in and V ref, V out will be at V ref. There'll be no difference between V out and V ref, and it's really the difference between V in and V ref that gets amplified by the gain. This will be plus A times V in minus V ref, where A is the gain, and that's equal to the reciprocal of our voltage divider ratio, R1 plus R2 divided by R2. Sometimes you see this written as 1, just dividing the R2 into R2, plus the ratio R1 to R2. Okay, that's how the inverting or the non-inverting amplifier worked. And we're interested in knowing what is the sensitivity of the gain A to R1 and to R2. Well, the sensitivity of A to R1 is going to be R1 times D log A dR1. Okay, so A is in this form, R1 plus R2 over R2. And if we like, we can use the property of logarithms to write the log of that ratio as the difference of logs. And so this is equal to R1 times D by D R1 of log R1 plus R2 minus D by D R1 of log R2. Okay, so this is R1 times D by D R1 of alright, can do the derivative here. So the derivative of a log is 1 over the thing in parentheses here, so it's 1 over R1 plus R2 times the derivative of the argument with respect to R1. Well, that's going to be just 1. Right? The sum of R1 and R2, dR1, is just 1. And we have minus, well, get 1 over R2, and then dR2, dR1, that's just 0. Okay, so this is just basically R1 over R1 plus R2. And we can try to express this maybe in terms of the gain, A, that may be more convenient, by noting that R1 over R1 plus R2 is equal to 1 minus R2 over R1 plus R2. Right, so if I put these over a common denominator, the R1s or the R2s would cancel, and I would get R1 over R1 plus R2. And of course, this is just 1 over A. So this is just 1 minus 1 over a, or we can write that as a minus 1 over a. Now we can compute the sensitivity of a with respect to R2 by R2 times d log a dr2. And again, using the same trick of expressing the log of the ratio as the difference of logs, we can write this as R2 times d by dr2 of log r1 plus r2 minus d by dr2 of log r2. So this is going to be r2, and we're going to get 1 over r1 plus r2 again, times 1 again, for the first term. Then we get a minus 1 over r2, but instead of times 0 now we have times 1. And so we can multiply the r2 through, and we get r2 over r1 plus r2, and we get a minus 1. So the r2's cancel in the second term here. So this is equal to r2 over r1 plus r2 minus 1. And of course this is just 1 over a minus 1. Which is equal to um, 1 minus a over a. And notice that these are just inverses of each other. So this is equal to minus the sensitivity of a with respect to R1. That's interesting. We have here that these two resistors contribute to in opposite directions to the sensitivity of the gain. So if R1 goes up by a certain per unit variation, that affects A in one direction, and if R2 goes up by that same amount in per unit variation, it would compensate for the per unit change in A that R1 contributed. So that's kind of funny. They will affect the gain in opposite ways. And so that's something we didn't see with the resistors in series or the resistors in parallel example. So that naturally leads to the question of how do these per unit variations in our components combine to form the per unit variation or the tolerance in some component, some parameter that we care about in the system, like in this case the gain of the amplifier. And that'll depend on how we combine them with the sensitivities. Will depend on kind of what we're interested in knowing. So if we're looking at, let's say, the tolerance on our resistor values and how that will contribute to, say, a tolerance, how they combine to form the tolerance of our gain, that's one question we might be interested in answering. Another question we might be interested in answering is something like, okay, given the resistor values, each of these resistors has something called a temperature coefficient. So if the temperature goes up, that affects these resistors in a certain way. The resistance changes a little bit. And how does that change in an environmental variable change the overall parameter that we're interested in, like the gain of the amplifier? In that case, we know we know that the temperature is affecting the resistors in sort of the same way, and so the fact that they compensate is good. But if we're interested in some sort of statistical variation in the parameter values, we don't know whether that variation is going to be positive or negative, and so we're interested in knowing something about sort of a worst case variation, or maybe some model for the variance or the standard deviation of our component values. Okay, so if we're interested in looking at tolerances, how the tolerances of our components combine to form the tolerance on some parameter, we can be thinking about sort of one of two different things. So how do per unit sensitivity or per unit sensitivity and tolerances. So there's sort of two different notions here. One is something called worst case variation. Okay. In this case, we might have something like our resistors are 1% tolerant, so they're guaranteed by the manufacturer to be to have a value that's within plus 1% to minus 1% of the specified nominal value. And if we have something like our amplifier gain being made up of two 1% resistors, we might want to know, what is the worst case variation we could expect from our in our gain based on the extreme values that we could expect to have for our two resistors or something like that. In that case, let's say the tolerance on Y will be the worst case tolerance on our parameter. That's going to be equal to the sum from I equals 1 to n of the absolute value of Sy xi times the tolerance of xi. Okay, we use the absolute values.
For help with that question, go to the help and feedback section of the Alexa app.
Thank you, Alexa. I appreciate that. That's very helpful. So T, Y, and Txi are the per unit tolerance of the parameter y and x1 up to xn. Right, so this would be like the 1% tolerance on the resistors, so that'd be like 0.01, and the way these combine is with the absolute values of the sensitivities. So I don't know if the variation is, in worst case, going to be positive or negative in the way that it conspires with the other tolerances, but I can't have a best case scenario where I've got a positive sensitivity and a negative sensitivity compensating each other. I need to be pessimistic because the worst case variation is going to be where the signs of the tolerances, the worst case variation that I can expect from my component values, will conspire with the sensitivity signs in the worst case, and so I take the absolute values here to account for that. If I'm interested in modeling the statistics of y, I might be interested in knowing something like what is the standard deviation I can expect for my parameter y normalized to the mean as a function of the standard deviation of the components normalized to their means. Standard deviation / coefficient of variation. So this is a second sort of sense of this whole sort of tolerance idea. So the coefficient of variation, denoted usually CV, for a variable is basically the standard deviation, call it CV, is a standard deviation divided by the mean for some statistical quantity, or some parameters subject to some statistical variation. So this is the mean, this is the standard deviation. So this is not a course on probability and statistics. We're basically just going to state some results, but what we would find is the coefficient of variation for our parameter of interest y is going to be equal to the square root of the sum from I equals 1 to n of sy xi squared times the coefficient of variation of xi. So this is assuming the xi are statistically independent. So the way that these coefficient of variations, which are sort of like normalized variation, combine for a parameter that is determined by the sum of those, will be through the square root of the sum of the squares. This is actually squared. So it would be the variance of y is equal to the sum of the squares of the variances of our parameter values. And so the way that these sensitivities come into play is that they weight the variances by their squares. And of course, this worst case variation, the square root of the square of the sensitivity is just the absolute value of the sensitivity. And so we have something like the triangle inequality here that suggests that the worst case variation is going to be more pessimistic than this sort of more statistical idea here. Anyway, so if you know something about the means and the standard deviations, you could use something like this to combine the coefficient of variations with the sensitivities to find the expected coefficient of variation in the overall parameter we're interested in. If you're interested in worst case, you could be a little bit more pessimistic and basically take these per unit variations in the parameters and combine them with the absolute values of the sensitivities. Okay, that's going to be it for this segment. In the next segment, we'll look at some actual measured data on some resistors that's been taken in the history, over the history of this class. and also some experimental measurements of variation in 1% metal film resistors that was taken by Dave Jones of the EEV blog. And we'll take a look at and see how we'll take a look at some actual data about how resistors vary. Till next time.